It's a pleasure to be with you to present this final lecture, number 8, in the powerful and compelling 6 classes series. Let's begin by putting into perspective where we are today and where we're heading in the future. I'd like to open with this slide because it's a picture of Apollo 8 on the first Earth Day, April 22nd of 1970. It really shows how very small, finite, and fragile our planet is. It is also a way to help us understand how truly naive our early concepts were when it came to the idea that the solution to pollution is dilution. That was unrealistic, and given what we've learned over the past several decades, it's easy to see why that's the case today. You'll recognize this slide is one that Arlene Bloom has used each week in this lecture series. For the past 6 weeks, you've heard about those 6 classes of chemicals. And we now know for certain that these classes of chemicals have adverse impacts on human health and our environment. Today I'd like to discuss 2 things with you. First is a high-level overview of what the global impact of these chemical classes looks like. And second, more importantly, what would you do to change the negative narrative and turn it into a positive one using the power of green chemistry? We can help reduce past impacts, but more importantly, we can avoid the creation of new negative impacts in the future. We call those unintended consequences, and we now know how they can be avoided. The big question we have to ask ourselves is, do we need it? You'll recognize that in the talk given last week by the former director of the California Department of Toxic Substance Control, Debbie Raphael, the key question we should be asking is, do we really need it in our products or in our formulations? In many cases, the answer to that question will be yes. So let's examine for a moment the state of chemistry and its impact. We can all list the remarkable contributions that chemistry has made to our modern world. Unfortunately, there have been some negative consequences. Modern chemistry has been practiced for the last 250 to 300 years. Over that time frame, mankind has mastered atomic theory. We've learned to manipulate atoms and molecules. And in fact, today we can create any molecule pretty much that we can conceive of, many of which have never existed in nature before. Mankind has been able to build this global chemical enterprise through the use of petroleum. We've harnessed the potential for petroleum both to create energy and also to create these new building blocks. As a result of chemistry, we've revolutionized agriculture, and with that, an ability to feed the 7+ billion people on our planet today. It would not have been possible without the results of chemistry. We have built chemicals that are better, stronger, cheaper, and more durable than have existed in nature. However, in many cases, this means they do not biodegrade and thus can persist in the environment. We know they can accumulate in the food chain and build up in living systems. If you look at slide 8, it's an estimate of the global chemical enterprise. $4 trillion, or 4 with 12 zeros after it. I don't know about you, but I have no ability to put a number that large into perspective. Arlene referenced the 85,000 or so chemicals that are approved for commerce in the United States. The vast majority of those chemicals have never been tested for human health or environmental impacts. If you look at the Chemical Abstract Service, which tracks new chemicals, you'll find that there are more than 75 million unique substances around the world that have been registered with that service. The vast majority have never been considered from an environmental or human health point of view. If we go to the next slide, we can wrap up this discussion by simply saying, I believe everyone on the line today is familiar with some of the unintended consequences of these tens of thousands of chemicals that are used globally on a daily and regular basis. And we won't talk about the details of this slide other than to say that these phenomena are well documented, well known, and is the reason we have to ask the question, do we need it? I like to say that in the eyes of nature, our current business models are not sustainable. When we ask ourselves the question, do we need it? When the answer is yes, I think it's fair to say that there is a better way. If you look at this slide, You've probably heard the quote from Einstein, "Insanity is doing the same thing over and over again and expecting a different result." I'd like to turn that around and say, what can we do differently that would result in a different outcome? How can we reduce the potential for adverse human health and environmental impacts? How can we eliminate unintended consequences? How can we end the concept of regrettable substitutions when we know we have a bad actor, when we substitute it for something else without going through the proper testing protocols, only to find later that we regret the fact that this chemical has its own unique set of human health and environmental impact problems? We can choose to make a difference in how we practice chemistry in the 21st century. But how do we do that? Well, if you look at slide 12, we have this concept called green chemistry. Green chemistry has actually been around for over 20 years, but only in recent years has it really begun to gain traction. There is growing recognition that it does offer us a viable, powerful, and proven alternative. I've given the definition of green chemistry here as the design of chemical products and processes. So how can we make the chemical as well as the chemical itself in a way that will reduce or eliminate the use and or generation of hazardous substances? You'll notice that it doesn't just focus on a particular product. It focuses on the chemical, it focuses on the process, and it focuses on all the other substances involved in the chemical reaction or transformation. It's probably fair to say that no chemist sets out to design a material that they know will be bad for human health. Then again, as a PhD chemist myself, I suspect many on this line would agree, no chemist in their formal training is ever taught to ask these kinds of questions. They are also not given training in the tools necessary to do the analysis of impact. That's where green chemistry comes into play. It's one thing to talk about a definition, but how do you actually implement that concept? Well, if we look at the next slide, it outlines the 12 principles of green chemistry. By applying these basic principles, and if you look at them, many of them are based on common sense, you can challenge yourself to do chemistry differently in the future. You do not have to use all 12 principles all the time. Applying one may be sufficient. But take a step down this new path and make a positive impact as we move forward. It provides a wonderful roadmap for a chemist or an engineer to ask key questions about chemistry and ask him or herself, how can I do it differently to avoid these problems in the future? If you look at the next slide, you'll recognize this as the standard periodic table. The number plus or minus 88 indicates there's about 88 chemicals in the periodic table that are used more or less by the chemical complex worldwide. There are more elements than that in the periodic table, but there are about 88 or so that we use routinely in the chemistry that we practice. Those 88 are the building blocks used to make the 85,000+ chemicals that are approved for commerce in the United States, and more importantly, the 75 million unique compounds that have been registered in the database I referred to earlier. If we look at the next slide, you'll see an interesting comparison. The elements highlighted in green there represent those elements that are used by nature. That's not to say that nature doesn't occasionally use one of these other elements, but by and large, all of the molecules, all of the functions and services that are delivered by living systems found in nature and in our environment are the result of the use of these about 12 chemicals in the periodic table. We know that nature has had 5 billion years to engineer some rather elegant solutions to many rather challenging chemistry and engineering problems. And we can learn from those lessons. I'm going to give you a few quick examples. The next slide is an example of what we call the Peacock Effect. Everyone is familiar with the wonderful plumage and colors of the peacock. When scientists look at detail at the molecular level, what we find is a very fine microstructure. In fact, that structure is at the level of the nanoscale. And nature provides this color without using a dye or a pigment, but actually by building mechanical structures on the same scale as the wavelength of light. Nature has been able to manipulate the light that is reflected and refracted to produce these vibrant colors, and not having had pigments or dyes used to do that. Of course, you know in the chemistry world we tend to use dyes and pigments to get the colors we want. This is a big lesson we can learn from nature, how to create color without having to use chemical dyes in the process. The next slide is another example of a gecko. We all know that geckos can stick to a surface. In fact, they can hang upside down from a ceiling, and they don't use what we would think of as traditional adhesives to accomplish that objective. Scientists have now taken a close look at the feet of geckos in trying to figure out what goes on a molecular level that gives that gecko its ability to hold on. When we try to mimic this process, we refer to it as biomimicry. In this slide, you'll see a close-up of the feet of the gecko. And in fact, we now know how the gecko sticks to these surfaces. In the chemistry world, we call it van der Waals forces. So if you're not a chemist, don't worry about that. But it's the interaction between the molecules that allows this adhesion to occur. If you look closely at the foot of the gecko and look very carefully, they have individual toes on their feet. And each one of those toes has finely divided ridges that we call setae. You could see those ridges in this close-up photograph. And each one of those setae has about 500,000 or more little fiber structures called spatulae. And all of those individual spatulae create a huge surface area. And when all those spatulae interact with the surface of a wall or a glass, it allows the gecko to hold on to the surface. Again, it's done without using any adhesives, so it's a really powerful lesson from nature. If we move to the next slide, you'll begin to see the impacts of green chemistry in the real world. So that 20 years ago invention is now getting wide adoption. You hear a lot about bio-based building blocks coming from rapidly renewable resources. All the molecules on the left-hand side of this slide, which are fundamentally important to the global chemical enterprise, have been historically derived from petroleum. Now, all of these materials also have a bio-based alternative to them. So when you're specifying chemicals in products or formulations, one of the things you can do is ask for the source of that material and have a preference to source bio-based feedstocks because they're rapidly renewable feedstocks and don't require pumping petroleum out of the ground. If you look at the right side, these are technical names for chemical reactions, how we make molecules in the chemistry world. The important part is not to understand the chemistry, but understand that when I was in graduate school, every one of these reactions and many more required an organic solvent. And we know that organic solvents in many cases are not good for human health and the environment. Today, every one of these reactions can be run in an aqueous system, which means we can reduce or eliminate both the manufacture of solvents and the use of solvents, which have many workplace exposures associated with them. Residual solvents in the products, which result in volatile organic compounds, can be removed. And at the end of life, in terms of manufacturing operation, you don't have solvents to deal with. We have water, and we can purify and reuse water again and again. On our next slide, you'll see a representation of a growth chart put together from an analysis by Pike Research, estimating the impact of green chemistry in the global marketplace. You could see here today, green chemistry on a commercial scale is relatively small, about $3 billion out of that $4 trillion enterprise I mentioned earlier. But in less than 6 or 7 years from now, we can expect to see this grow to $100 billion plus, and that's about a 48% compounded annual growth rate. So it says green chemistry is really beginning to gain traction globally. That's good news. And more of these tools and techniques and the products that they produce and the processes by which they are produced are going to become available to you as users and suppliers of this chemistry going forward. So let's talk for a minute about why this is so important. If we look at our next slide, the obvious thing is the reduction in human health and environmental impacts. But the drivers really are that society is beginning to become more sophisticated here, and they have these expectations. Corporations must continue to earn the right to operate, and moving down this path is a way to do that. Corporate reputations can be enhanced, cleaned up, and ensured. Interestingly enough, the application of the principles of green chemistry to the development of new products and formulations can lead to great innovations. Those innovations at the same time can drive competitive advantage in the marketplace. Certainly, as I've traveled around the world talking to young people, the young people get this. The folks that are going to do these jobs in the future, they are looking for companies that understand sustainability, the commitment to sustainability, and that are implementing the concepts of green chemistry, sustainable chemistry, and engineering as they go forward. So you'll have a great impact on a company's ability to recruit new resources. Finally, from a pure dollar and cents initiative, every green chemistry example that I'm aware of has resulted in reductions in cost, in the production of waste that has been handled and disposed of, in the use of energy to manufacture products and formulations, and in the consumption of raw materials. As a result, we're dramatically reducing the risk as we significantly eliminate or completely eliminate hazards associated with these new materials. I put a big equal sign with a dollar sign to say that the business community understands dollars and cents. And all of this green chemistry really equates with an excellent return on investment. And it's a proven approach. It's not an academic curiosity. In our next slide, you'll see just a quick bullet list of some of the watchouts I've run into as I've listened to people push back on green chemistry. Is the idea that you don't want unintended consequences. So you have to apply the tools and the analyses to avoid those regrettable substitutions. That's what green chemistry allows you to do. A lot of times, if you don't have a good leadership support, it's hard to move these programs forward. So you have to ask the right questions to be successful here. And you can read down the rest of this list, but a lot of time folks will say that no one's willing to pay for green. Well, in fact, it's a good part of the story. But if you don't have your economics right and your functionality right, it doesn't matter if you're green or not. Green is the icing on the cake that allows you to do all of those things I've talked about earlier in terms of why green chemistry is important. In the next slide, I'll talk about what you can do specifically to get started. As I bring to a close this section, I want to talk specifically about actions. So ask that important question. Do we need this chemical or in the formulation? And when the answer to that question is yes, seek the expertise. Apply the green chemistry that drives your alternative answers. Don't just pick something else off the shelf without knowing that you're not creating regrettable substitutions in the process. Work to get your leadership behind it, because most people respond to what leadership indicates as a priority. It's probably smart to try to hire people that are either trained formally in green chemistry or know where to go and tap into the resources. Make a personal commitment to take action now and to make a difference. Take the green chemistry pledge. No new chemical or process by which that chemical would be manufactured should be commercialized without a complete green chemistry screen for human health and environmental impacts. On our next slide, we can talk about specific steps for getting started. The first step for me is to find out what's in your products today. It's surprising to know that many people are not aware of what is in their products, and occasionally you'll get suppliers who say, quote, "That's confidential business information, so that's proprietary," quote. And I'd suggest to you that in today's modern world, anyone can take apart a product or formulation and know within a few days exactly what's in it and exactly how much is in there. So these arguments, in my mind, don't have as much merit as they used to in the past. Embrace that pledge we just talked about. Nothing new or replaced without modern testing protocols to ensure their safety from a human health and environmental perspective. Use the tools of life cycle analysis. These are sophisticated tools. It does require some expertise, so you have to hire someone or contract with someone to provide that analysis and that information for you going forward. Look at your products instead of just from cradle to grave, but look at cradle to cradle, where you bring it back and reuse it, or at least versus the cradle to grave approach where people throw it away and tend to forget about it. I like to ask students in my lectures, how many people have thrown something away? Some shoot their hands up and others are not sure if it's a trick question. But I say to them, think about this. Where is away? There is no away. You could say to your suppliers, we have identified certain classes of materials, for example, the 6 that are part of this seminar series, that we would like to have removed from our products. Give them a time frame, for example, the next 2 years. Then work collaboratively with your suppliers to accomplish that objective. There are some roundtables out there that you could become members of. The Formulators Roundtable and the Chemical Manufacturers Roundtable, a part of the ACS Green Chemistry Institute. They are a wonderful place where competitors come together and work toward the common cause of a rising tide floats all boats by reducing or eliminating hazardous chemicals in our environment. This slide talks about basically the logos of a whole family of tools out there that it will take some expertise to use. If you want to do this, there is one of 3 things you can do. You can hire someone that is skilled in the application of these tools. You can hire a consultant that can give you that expertise without a long-term commitment to a new employee, or you can say to your suppliers, this is what we expect and here's our time frame. These are some of the tools that can help us tackle these challenges to remove the products from our supply chain. Each one of these is listed with a link that connects them to the fact sheet that you will have at the end of this slide deck, and that will be posted. Some of these tools allow you to screen the chemicals you've got. Others allow you to look at specific environmental and human health impacts. Yet others allow you to look at life cycle impacts and help you design, using the principles of green chemistry, new chemicals for your products and your formulation. So if we switch to our next slide, again, back to getting started, it's important to create metrics. That's how you measure progress. Once you create those metrics, you create goals and look at your progress against those goals. Society is increasingly becoming more sophisticated about what's going on with the chemicals in their products, and they're expecting transparency. I encourage people to embrace transparency in your conversations with your suppliers and with your customers, and then commit to producing a sustainability report where you disclose your progress, your metrics, and your goals. See if you can find a senior management champion, which will make a huge difference in how rapidly you can advance against some of these goals. Don't be afraid to speak up and be heard. Reach out to those who are doing it today. I'm going to give you an example of successful green chemistry implementations on a large scale. You can reach out to those folks, and most of them are happy to talk about how they went about implementing the principles of green chemistry. If you have a challenge within an industry, for example, I hear a lot about concerns with the fluorochemicals that provide oil and stain resistance. As an industry, create a challenge. Put it out there to the academic world. They tend to be very responsive to these things. How can you apply the principles of green chemistry to create new chemistry alternatives to fluorochemical-based systems for oil and stain and water repellency? Finally, I'd say make a decision individually today, at this moment, to make a difference for your family, for your children, for your grandchildren, and for society, because the tools exist and we know how to deploy them. Let me wrap up here by giving you a couple of examples of the deployment of green chemistry on a commercial scale. All of these examples have been recognized by the EPA Presidential Green Chemistry Challenge Awards. The first is Procter & Gamble, who replaced petroleum-based oils in paints with an oil-based ingredient that results in a reduction in solvent usage of greater than 50%. Of course, paints are used to coat surfaces, and those are very high surface area sources of volatile organic compounds. By reducing the use of solvents, you can dramatically cut VOCs. The second example, BASF, is again related to painting. It's a primer used in automobile manufacture, and they were able to cut the VOCs in manufacturing operation by greater than 50%, and in the process eliminate a very reactive class of chemicals we call isocyanates. A side benefit that resulted was a drop in the amount of primer that's needed and a dramatic reduction in the amount of waste that's produced in the manufacturing operation. The third example is Shaw Industries producing a carpet tile called EcoWorks. Those tiles were able to eliminate several different components and are common in the carpet industry, in particular PVC. In the process, they created a carpet tile that is recyclable at the end of its useful life. Finally, the example from Kraton Performance Polymers. The technology called reverse osmosis is really critical in many places around the world, separating water from salt, producing safe drinking water. It's also used to do many other kinds of purification steps. Kraton developed a halogen-free membrane that in the process uses a lot less solvent to manufacture. As a result, we've eliminated the halogen component that's one of those 6 classes. A side benefit was a dramatic increase in the amount of water that can be purified and a significant reduction in the cost of the membrane and a dramatic drop in the cost on energy required to conduct the reverse osmosis process. I mentioned to you earlier, there's a great return on investment for green chemistry, and these are some excellent examples. Finally, slide 30 is the resource sheet. There's some general information here. There's a few textbooks listed. All of the tools I've shown on my earlier slides and a few more are listed here with their direct web links, and then some additional resources, including a link to the EPA PDF file that lists all the winners of the Presidential Green Chemistry Awards since the beginning of the program in 1997. There's also a link to a university site that provides some dramatic, useful information on green chemistry. So let me stop there just by saying, on the next slide, this beautiful scene of nature. We will not solve all of our problems at one time, but if we take small steps to get started at some point in the future, we'll look back at this marathon that we're running and realize just how much progress we've made.